The following is an excerpt from my movie, Dialectic. It explains science and the scientific method. We're going to have to swim around in the shallow end for a while I get us all on the same page with regard to exactly what science is. The guiding philosophy that underlies all science is known as the scientific method. The scientific method gives us a framework from which to design, conduct, and conclude results from experiments. And this is how we learn about the physical world. I'll give an example of a slightly oversimplified scientific experiment to illustrate how conclusions are reached by scientific experimentation. The scientific method consists of three parts, and it's the last part that's most frequently misunderstood. Step one is to create a falsifiable hypothesis. So for this demonstration, I'm going to say that it's going to be a container of water, and we want to determine if it freezes at 0 degrees Celsius or not. So step one would be to create this hypothesis, a falsifiable hypothesis. Either water freezes or it does not. Step two would be to perform the experiment, and that would be taking the container of water and putting it in a freezer and seeing if it does in fact freeze. Step three is to look at the container of water and see if it's frozen and draw conclusions from that. The tricky part is that if the water does actually freeze, then we can draw no hard conclusions. It only leads us to do more experiments on the freezing of water. If water does actually freeze, we have not proved anything, but also managed not to disprove the hypothesis. The results suggest that the hypothesis is a good one to try and falsify with another experiment. Someone else may perform the experiment that meets the above conditions and have water not freeze. Perhaps they try it without air pressure or without gravity. Maybe water doesn't freeze at 0 degrees in a zero gravity environment or in the presence of vibrations. Water freezing may be dependent on other factors, as far as we know. If the law that water freezes at 0 degrees Celsius is successfully falsified, then we make up a new hypothesis and continue the process of trying to falsify it. If water is observed to freeze at 0 degrees Celsius, then we perform more experiments to meet the above conditions in such a way as to continue to falsify the hypothesis. We try to make another experiment that meets the above stated conditions and have the water not freeze. We're always trying to disprove the original assertion. If we cannot create an experiment where water doesn't freeze at 0 degrees Celsius, then we accept that water freezes at 0 degrees Celsius as a scientific truth. This adopted rule is a maxim of understanding if it cannot be reasoned from known laws and is just an observation. Modern science is conducted with a lot more sophistication than the above slightly oversimplified example. The above example was created to show that truth is established by inference of not being able to nullify a hypothesis, not by being able to prove one. This does not create a law, it creates a maxim of understanding, which are used in the same way as laws and often referred to as such. So science illustrates falsehoods by finding out what isn't true. We find out what is actually true. We create understanding and maxims of understanding through empirical experience by performing experiments. Understanding forms half of this dialectic. The other half is reason. Physics can convert a maxim of understanding or a maxim of judgment into a law, something that is accepted as absolute truth using mathematical reasoning and deductions from something Kant calls a priori intuitions. An a priori intuition is an idea like the shortest distance between 2 points is a straight line, and that time always progresses, as well as deductions from these two propositions. Most basic principles of physics are based in reason. Newton's mechanical laws are based in reason, but the law of conservation of energy is really just a maxim of understanding because it cannot be deduced from reason alone. A priori principles only exist in physics and do not exist in other sciences. The scientific method can get us understandings and maxims of understandings because it's entirely based on observation. Theoretical physics gets us ideas from maxims of understandings and judgment generated by experiment into maxims of reasons, in other words, laws, by reasonable deduction. The best example of this is the old maxim of judgment that nature always takes the shortest route. It was later refined as the principle of least action and forms the basis for what we call classical mechanics, which is slightly different from Newtonian mechanics. In computer programming, the scientific method is called hacking. I can't recall who it was that said this so perfectly, but science actually hacks away at reality. Programmers use the scientific method only when trying to figure out what went wrong. The scientific method, developed by Francis Bacon, is the accepted method for observations because it's easy for us to expose lies or untruth, but difficult in principle to prove that something is true. This is why mathematical proofs are so difficult, and propaganda and general bullshit usually cannot stand up to even cursory examination. I'm not unscientific, but I like to know exactly what science and understanding can and cannot do for me. You need to know this to understand science. Everybody likes a hot cup of coffee in the morning before they go to work, and science gives us that comfort in life associated with material well-being. The faculty of understanding is the need and want part of consciousness or awareness. It is a slave to the senses. Understanding is the machine that's inside of each of us. Reason, on the other hand, gives us consciousness, freedom, practical moral sense, some physics, and all of mathematics. Reason makes us self-conscious of the machine. It makes us alive, and the ability to reason rather than just follow rules is the very thing that makes us conscious. Moral reasoning is said to separate us from the beasts by philosophers such as Kant. Personally, I think some of the beasts have reason and some of the people do not. Can science eventually determine absolute reality? If science cannot discern absolute reality, then a purely materialistic viewpoint of the world would be incorrect and an example of an overextended use of reason. Philosophers have been long saying that we are victims of an overextended use of reason. I'll now show another example of the use of the scientific method. I was given a demonstration to help them understand what science is and by extension what it is not, and to demonstrate the fact that science does not constitute absolute knowledge. Science requires that we examine phenomena that lies outside the domain of sensory perception in many cases. So to prove this, we're given a box that's painted and covered, and it contains an object inside. We have no idea what's inside the box. It's up to the student to experiment and determine what object lies inside the box. Now, the possible objects that lie inside the box are those that lie within the limits of the student's imagination. Let's just suppose that the student's imagination is limited to this picture. So all of the objects that he or she has ever seen is in this picture. So we look at the box, we shake it around, we listen to it, and we try to discount objects that couldn't possibly be the object that is inside the box. You feel the reaction of the box as you shake it around, you listen to the sound. Immediately you realize that the object makes a loud sound when it strikes the side of the box, so it can't be the eraser. You now know something about the object that's inside the box. You know that it's not an eraser. It doesn't feel heavy enough to be the nut, so it's not the nut. It makes the same sort of sound no matter how it strikes the side of the box. So the material is homogeneous. Whatever the object is made of, it's made of the same material throughout. So it can't be the bottle of glue, it can't be the USB connector, or the key. It's too heavy to be the pen cap. It rolls around in 2 dimensions, so I can feel it rolling around the box when I do this. But if I do this, I see that it doesn't really roll. So it must be a circular object. So it must be the coin. It has to be the coin, given what we know. Now, the idea of it being a washer would never occur to the student because the washer lies outside the student's experience. Never seen a washer. Therefore, it's a coin. Now, as a scientist, the scientist would inform the engineers that it's in fact a coin that lies inside the box. And the engineers would draw conclusions from the fact that there's a coin inside the box. They know that if water gets inside the box, it won't affect the material properties of the object that's inside the box, because if a coin gets wet, it doesn't matter. Now, this is really how science is done. Now, in the case of the cell, a molecular cell, it's really too small for us to see. And for a long time, scientists assumed that the cell was a very simple biological object. But now they've learned that it's actually really, really complex. And the same goes with the atom. 100 years ago, they thought that the atom was composed of 3 particles, the proton, the neutron, and the electron. And now they've seen that the atom, in fact, contains many more objects than just protons, electrons, and neutrons. And Kant, in the Metaphysics of Natural Science, explains that the atom would get more complex as time goes on, as scientists did more and more experiments on it to try and determine its ultimate composition. Kant explained that they would never know the absolute composition of the atom, but that the models will get more and more complex as they try to explain more and more experimental phenomena. So that is the nature of science. It doesn't lead us to absolute truth, but what it does is discount possibilities. And in that sense, by knowing what isn't true, we find out what is true. We are ultimately limited in our knowledge of the outside world by our senses. If we cannot see it, hear it, smell it, taste it, or feel it, then we're left only with our imagination. Imagination can only be based on prior experience. We can only imagine things that we've already seen. You can't imagine anything in the box except objects that you know of or combinations from prior experience. People assume that ideas like quantum mechanics and relativity can reach into a reality that is beyond sense, but really these are only models, tools that can only be an aid in ultimately describing the experiences of our sense perceptions. Theories must be verified by experiment, and this prevents the science from reaching beyond empirical experience and into the great beyond. Science is the model for what is inside the box. Are electrons real? What's a magnetic field? Gravity? No one actually knows. It's the hypothesis of the nut, assumed to be in the box, the hypothesis that no one has ever proved to be wrong. We may not know what electricity is, but we can see how much is flowing in a circuit for the purpose of how we understand it with an electrical meter. Evidence of what we imagine as electron flow is in the movement of the meter. Electron flow is converted to sense perception using the meter. A light bulb, radio, or television set gets us to see the effect of what we call electricity. None of these observations are observations of electricity itself, only its effect on our senses. Kant, in his short book, The Metaphysics of Natural Science, explains that for physics itself to exist, the world must be assumed to be comprised of small particles rather than homogeneous matter. Without this idea, science cannot stand on the laws of physics. Matter is already assumed to be composed of small particles before the game of physics even begins. Science is now structured across fields. There aren't many natural masters of all trades, such as in Kant's day. In Kant's day, scientists would deal with subject matter as diverse as, say, fire and anthropology. We now live in an age of specialists. Consider anthropology, since Kant was an anthropologist throughout most of his academic life. If we are to be systematic and non-self-contradictory in science, then what is true in anthropology must also be true in biology, and this must also be true of chemistry. What is true in chemistry must also be true of physics. What is found in experimental physics must be true in theoretical physics. Famous theoretical physicist Leonard Susskind, in a YouTube video, explains his field, which is theoretical physics. I've long lost the link to this video. He explains that whenever they run into trouble with their scientific experiments and things don't really quite add up, they always return to Maxwell's equation. equations. Maxwell's equations are the well-known bedrock of science. Maxwell's equations completely describe the behavior of electricity and magnetism. No one can tell exactly what an electron or a magnetic field is, aside from a quantitative description of observations. Maxwell's equations explain electricity as we experience it. They completely explain the science behind electrical power, the internal operation of a computer, a radio, and all things electric that we can build or experience. These equations comprise the only model in science that works in both the quantum theory and in the theory of relativity, often attributed to Einstein. Maxwell's equations form laws. They are based on reason, although discovered with experiment. Science is a path to understanding the physical world. Science is built on one half, the understanding of this possible dialectic, that I'll illustrate. Sometimes physics bridges the gap and converts a mere maxim of understanding into a law through deductive reasoning. Reasoning forms the other half of this dialectic. But mostly science is just observed phenomenon, which creates only maxims of understanding. We know that it's true because that's what always happens, but we can't deductively show why it happens. I'm going to illustrate the basic Kantian hypothesis that the world does not exist as we see it, using very well-developed and abstracted pure hard science, Maxwell's equations. I'm going to demonstrate a dialectic that occurs between reason and understanding in the scientific world with a physical example to explain this dialectic before I go on to use the dialectic to look at other things, so that we can get a concrete idea of what the dialectic actually is. I'm going to use an animation to explain this paradox. To illustrate this problem, I'm going to show some animations of how electricity works, as how we know and experience it. Maxwell's equations describe electricity and magnetism operating in any circumstance or system. Everything known about electricity and magnetism is summed up in those four equations. They are complex, and no one uses them in the above form. They are used to create abstract models, something Kant called schematism, and these abstract models help us understand the system that we are thinking about in a simple but perfect and complete way. Now I'm going to illustrate one of these models and explain it in the following animation. Here an electric circuit is illustrated. Potential energy is stored in the battery. The electrons, the negative charges, the black particles have a propensity, a potential to move around the circuit to equalize the positive charges at the other pole of the battery, so that the net charge is zero. They cannot always, because there is no path with a low enough resistance for many of them to do this. Nothing happens until we close the switch and the electrons flow in the circuit. As the electrons travel a path, they experience resistance in the light bulb. Resistance, the electrical form of friction, heats up the element in the light bulb, causing the element to glow and give off heat. Potential energy stored in the battery is being converted to heat and light in this circuit using the properties of the filament in the light bulb. The battery slowly drains as its potential energy is drained in lighting the light bulb. Its potential energy is converted to heat and light inside the light bulb, in the filament of the light bulb. This shows how energy is stored and used from a battery. There's another type of storage device used in electric circuits called a capacitor. A capacitor stores and releases energy much more quickly than a battery. Capacitors lose charge quickly, even when they are not on, which is why they don't get used as batteries. We can charge a capacitor with a battery, transferring a very small amount of potential energy from the battery to the capacitor. To charge the capacitor, we must flip the switch to give the electrons a path to flow. There's always a little bit of resistance in any circuit. Here it's represented by the rectangular black object in the circuit path. As electrons flow through the resistance, they lose energy and create heat. The energy from the battery is being transferred to the capacitor, but in the process some energy is lost due to the heat generated by the electrical resistance in the resistor. Eventually, the capacitor gets charged so it has the same voltage as the battery. The capacitor doesn't require much energy from the battery to become fully charged. so the battery has lost a very small amount of energy to fully charge the capacitor. Batteries can store a lot more energy than capacitors. Electricity stops flowing when the electrical pressure of the capacitor matches that of the battery. This pressure is called voltage. We can make an electric circuit that will charge one capacitor from another capacitor, but nothing happens until we close the switch to complete the circuit. Let's start the circuit with 3 units of charge on one capacitor. We close the switch to begin the charging process. Notice that we lose a bit of charge, the energy in the circuit, through the resistance. We started with 3 units of charge on one capacitor and finished with 1 unit of charge on each capacitor. We lost a unit of charge, a unit of potential energy, to heat buildup in the resistor. Everything works according to Maxwell's equations. Every circuit contains resistance. But if there was no resistance in a circuit, our circuit would look like this. Still, nothing happens until we close the switch. A circuit with no resistance cannot exist in experience. If Maxwell's equations, the foundations of science, are absolute truth, then they must express truth regardless of conditions. Maxwell's equations can be tested on a circuit that does not contain any resistance because some of the derived formulas do not contain resistance. So, what happens when we close the switch in this ideal circuit that should behave according to Maxwell's equations? When we close the switch, charge transfer takes place immediately. The charge is split between the 2 equal capacitors instantaneously. Capacitors store charge. A capacitor of 1 farad holds 1 coulomb of charge when it is fully charged from a 1-volt battery. The equations derived from Maxwell are Q, the charge, equals C, the capacitance, times V, the voltage. The energy in the capacitor is 1/2 times C times voltage, which is 1/2 CV squared. These 2 simple formulas are mathematically determined from Maxwell's equations. They change Maxwell's equations into a simple form for this simple circuit, but with no loss of information or accuracy. If the world truly exists as science shows us, then scientific laws are always valid. If science can lead us to absolute truth, possible truth outside of experience, then those laws can contain no possible contradiction. If there is a contradiction, then this accepted science does not reflect absolute truth. Maxwell's equations work for computer chips, power distribution systems, and in radio. They are valid in both the quantum and relativistic domains in physics. You cannot get energy from nothing is a scientific law. Energy cannot be created or destroyed. Most perpetual motion experimenters throughout history have been forgotten. Their ideas do not work, so they get forgotten and the experiments get repeated. But it's not always clear exactly why their experiments aren't working properly. If these 3 laws, the charge equals the capacitance times the voltage, energy is 1/2 the capacitance multiplied by the voltage squared, and energy cannot be created from nothing, cannot all be true outside of possible experience, then science cannot be said to lead us toward an absolute truth. Not everything can be explained with science. We can test the 3 laws to see if we can get a contradiction. If we make a thought experiment of possible conditions that may exist outside of experience, yet still be valid according to Maxwell's equations. In experience, we know that all electric circuits contain resistance. Sometimes it can be very low, but it is always present, even with superconductors. It can be practically zero with superconductors. This circuit does not have any resistance. We can test the Maxwell's equations and see if they reflect absolute truth outside of possible experience. In this circuit, the capacity of the capacitor to hold a charge is 1 coulomb per volt. This capacity is measured in farads after Faraday. If we increase the voltage on the capacitor, a greater charge builds up on its plates. If we apply a 1-volt charge to a 1 farad capacitor, it will hold 1 coulomb of electric charge, which is one heck of a lot of electrons. If we charge this 1 farad capacitor to 2 volts, we have 2 coulombs of charge built up on the plates. The charge of 2 volts is held on one of the capacitors because the switch is open. No current flows, nothing happens in this circuit. We close the switch and half the charge immediately goes over to the other capacitor. The charge transfer occurs instantly because there is no resistance. There is no energy loss because there's no resistance. Resistance is like electrical friction and creates heat when current travels through it, and heat is energy, so energy is lost. If there is no resistance, no energy can be lost. This circuit is an ideal circuit in that it contains no resistance and lies outside the range of possible experience. Let's see how those scientific laws that we accept as being absolute truth hold up in this thought experiment. The circuit in this state has a 1 farad capacitor charged with 2 coulombs of charge, electrons. The capacitor was charged with a 2-volt battery. The amount of energy can be calculated. It's 1/2 times the capacitance times the square of the voltage, which is 2 joules of energy. So there's 2 joules of energy stored in that left-hand capacitor. So here's the kicker. Since energy cannot be created from nothing, we expect the total energy in the circuit to be the same after we close the switch. The charge will just be divided between the 2 identical capacitors. The single 1 farad capacitor was charged with 2 coulombs of charge from being charged with a 2-volt battery. So the total energy stored by the first capacitor is 1/2 of its capacitance multiplied by the square of the voltage, according to Maxwell's equations. This means that 2 joules of energy are in the first capacitor before the switch is closed. So let's see what happens when we close the switch. When the switch closes, the charge is instantly divided between the 2 capacitors. There's no time delay because there's no resistance. This happens instantaneously. The charge is constant. It's just divided between the 2 capacitors. Connecting the 2 1 farad capacitors like this makes the total capacity of the circuit 2 farads. The voltage is halved because the charge must remain constant and the capacity is just doubled. According to the same energy formula, we have 1 joule. So in the initial circuit we had 2 joules of energy. In the final circuit we have 1 joule of energy, with Maxwell's equations not being able to explain the loss of energy. Now this circuit is a thought experiment that lies outside experience, but Maxwell's equations in this particular application do not include resistance, so we expect them to work within experience with circuits that have resistance as well as circuits that do not have resistance. So what just happened? When the box is closed, we make experiments and observe the following laws, which are in no way self-contradictory. We have the 2 formulas from Maxwell's equations. These equations are accepted as fact in physics, but there are some instances with electrical engineering and power systems where we run into this problem. Now, I don't know that much about that end of it, and it's really not the point of this video. The point of this video is to show a contradiction that lies within Maxwell's equations. Everything in the physical experiential world adds up, at least so far. When the box is open to look beyond experience, our laws become self-contradictory. They do not tell us what is in the box, only what we can observe. The scientific laws of Maxwell's equations only apply to the world of experience, give no hint regarding absolute truth in any sense. I've just proven that science cannot meet the requirement of showing us absolute truth by showing that science can be self-contradictory outside the bounds of possible experience. This creates a dialectic at the very base of science. I will return to this example again, so don't worry if you didn't get it perfectly. If reason and understanding and science can be dialectical on the very purest side, then we cannot say that either reason or understanding permits us to see the world as it truly is. This is a demonstration of the basic Kantian hypothesis, that the world cannot exist as we see it. And this demonstration wasn't known in Kant's time. I've just proven that science cannot meet the requirement of showing us absolute truth, by showing that science can be self-contradictory outside the bounds of possible experience. This creates a dialectic at the very base of science. I will return to this example again, so don't worry if you didn't get it perfectly.